So in this question, we're told to assume that friction is negligible. A small car with a mass of 20 grams is released from rest at a height h equals 1.50 meters above the base of an inclined plane leading into a loop. The radius of the loop is r is equal to 10.0 centimeters. So this is the same situation as what we saw with the Hot Wheels car, which came down the ramp and then went round the loop. So part 1, what is the speed of the car at the bottom of the incline? Part 2, what is the speed of the car at the top of the loop? Part 3, does the car make it around the loop? Okay, so we'll start with answering part 1. So we are trying to find the speed of the car at this blue dot here. So it started at the top of the incline, traveled down the incline. So as it did so, it dropped in height h. Now the easiest way to approach this question is through energy conservation. So the initial potential energy of the car plus the initial kinetic energy of the car is equal to the final potential energy of the car plus the final kinetic energy of the car. And what makes this easy in this case is that we know that the initial kinetic energy is equal to 0 as it starts from rest, and we can define the final kinetic potential energy as 0, as we can say, well, h equals 0 at the bottom here, and h is equal to h at the top. So we've got that the initial kinetic energy, which is mgh, is equal to the final kinetic energy, which is a half mv squared. So these m's cancel out, and we can rearrange it to get v squared is equal to 2gh, which tells us that v is equal to the square root of 2gh, which is equal to the square root of 2 times, let's use 9.81, times h, and h in this case we were told was 1.5 meters. So we can then solve that on the calculator, and we get 5.42 meters per second. Okay, part 2 then says, what is the speed of the car at the top of the loop? Okay, so now we're trying to work out the speed at this purple point here. What we'll need to do is use this equation again, the initial potential energy plus the initial kinetic energy is equal to the final potential energy plus the final kinetic energy. But what's a bit harder now is that the height of the car at this purple point is not 0. We've got r there and r there. So this tells us that the height is equal to 2r. So probably the easiest 2 points to use, because we need an initial point and a final point, we could use the bottom of the ramp here because we know what the kinetic energy is, but it's probably slightly easier to use the top as our initial point. So at the top, we know that the kinetic energy is 0. That hasn't changed. So we've got mgh plus 0 is equal to the final kinetic energy. Now, the potential energy is given by mg times the height, and this is mg times 2r in this case, because the height is 2r, plus the kinetic energy, which is a half mv squared, which is what we're trying to find. Okay, now I'm just going to scroll this up to give us a bit more space. Okay, so the m's will all cancel out, and what we're trying to get is this speed. So we can say v squared is equal to 2gh minus 2g times 2r. So this is equal to 2gh minus 2r. And so v is equal to the square root of 2gh minus 2r. And now we can just substitute in our values. We've got the square root of 2 times 9.81 times h, which was 1.50, minus 2 times r, which is 0.100. We need to substitute the R in meters, as the H is in meters, and we should use SI units. So then solving that on the calculator, we get 5.05 meters per second. So that's the speed at the top of the loop. Okay, part 3 then says, does the car make it around the loop? So for that part, we'll need to consider our forces involved. So here's our loop. Now at the top of the loop, here's our car. We've got a net force given by mv squared on r. That's the centripetal acceleration, the centripetal force, sorry. And that comes from a weight force, mg, and a normal force. And we have that the net force mv squared on r is equal to mg plus the normal force, and it will make it around if the normal force is greater than 0. If the normal force is less than 0, then that's indicating to us that the car has lost contact with the loop. So to have n greater than 0, we need to have mv squared on r is greater than mg. So we can cancel out the m's. So this tells us that we need v squared on r greater than g. So let's calculate v squared on r. So v squared on r is equal to 5.05 squared over r, which was 0.100. So this is equal to 255 meters per second, and this is greater than g. So this tells us it does make it around the loop.